this video, I'll be making a physics-based arcade-style car controller, using a fascinating concept. It works by having the player control a sphere that the car then follows around the scene. We'll start by creating a new project using the built-in render pipeline. We'll do this by clicking the 3D icon and we'll give this a name. Once it's loaded, we'll start with the default layout and an empty scene. We'll rename the scene to something other than sample scene. For our main camera, we'll set the clear flags to solid color, and like always, I'm going to be using a dark gray. For the directional light, we'll get rid of the yellow hue, and we'll reduce the intensity to something like 0.75. We'll quickly fix this game window by setting its aspect ratio to 16:9 because I'm running 1920 by 1080 for my resolution. Now lastly, let's set up the environment by giving the car something to drive on. We'll create a new empty game object called environment, making sure that its transform position is completely zeroed out. And as a child, we'll create a plane and call it ground. We'll set its scale to 50 by 50. Now let's create a materials folder inside our project window. And we'll create a gray material to drop onto our ground object. For this project, I'm going to need a car model, and I chose to use this free asset on the Unity asset store called Arcade Free Racing Car. And I also need an environment piece to test the car, and I'm going with the low poly road pack. Both of the links will be in the description. So before we set up our car, let's go to our package manager and import these assets. To begin creating our car, we'll go to the hierarchy and create a new game object. We'll make sure that its transform position is zeroed out as normal, and we'll name this object car. We'll navigate to the arcade free racing car and go into the prefabs folder. I'm going to use the red car. So we'll just grab this guy and pull him straight into the car game object. And we'll check the transform, making sure it's zeroed out. Now we'll focus in on the model. I notice the rear wheels are out of position. To fix this, we'll start by unpacking the prefab and make this its own game object. We'll expand it out and find the rear wheels. We'll position these and do the same for the front wheels. Now we'll rename it to car model since it's only the graphics and our logic will be on the parent game object. And then we'll collapse it back up. Now we'll make the sphere that we'll actually be controlling. We'll go to the root car game object and create a new sphere. We'll call this guy motor sphere. Since we'll be using physics forces to actually move this thing, we'll need a rigid body component. And we'll set its drag to 4. Now we'll go into isometric view to see what we're working with, and we'll need to align the sphere to the top of the ground. By holding control while I drag, it'll snap in increments and I can get it lined up. Now let's exit out of isometric view and get ready for the script. I noticed I put my materials folder inside the scene folder, so let's drag that out and into the main asset folder. Now inside our asset folder, we're going to create another folder called scripts. Now inside the folder, let's create our car script and we'll name it car controller. Give it a second to compile and then we'll drag that onto our car game object. We'll double click the script and let it open. We'll delete the comments right fast. We want to get the player's input, then we want to move the sphere, and then we want the car to follow the sphere. We're going to work backwards for a minute because with this setup a few problems arise. So first we'll set our car's transform to the sphere's transform, and to do that we need a reference to the sphere's rigid body. So we'll say public rigid body and we'll call it sphere RB. Now in the update, we'll set the car's transform position to the sphere RB's transform position. We can do that by saying transform.position equals sphere RB.transform.position. So let's Control S to save, and then we'll head back into Unity to playtest. So before we play, let's go to the car and make sure to drag motor sphere into sphere RB. Well, that's not good, is it? With a better look, nope, still ain't good. So let's investigate. We can see our sphere is here and our car is here. We can see they aren't lined up at all, but in fact, if we switch the car to pivot, we'll see that its pivot is at the very bottom. So here's the car set up, and its pivot point is right here. When we press play, the pivot snaps to the sphere. But here lies the problem. The sphere is also parented to the car, so now the sphere is trying to be pulled back to its original position. This causes the sphere to bounce back and forth between these two positions, and since it's a physics object affected by gravity, at some point it falls low enough that when it gets snapped to the position it was as a child object, it clips through the floor and the car disappears into oblivion. So let's fix this problem. We want the car's pivot point and the sphere's pivot point to be in the same location. With the pivot mode still selected, I'm going to grab the car and move it up to where I think I remember the center of the sphere being. Holding control will allow us to snap and make this a bit easier. Now this also moved our sphere, so let's select it and put it back right above the ground. So if we switch between the car and the sphere, we can see now that the pivots are aligned. If we check the transforms of these objects, you'll see that the car is at 0.5, but the sphere says 0. And that's because that's the sphere's local position to the car. If we pull it out from the car for a second, we'll see that both transforms are indeed 0.5. So let's parent that back under the car, and now all we need to do is select the car model and drag it back in place. So after all that, we can hit play to test. Now you'll see that the car doesn't bounce itself to death. Now we can go ahead and set up our input for our player. We can do this by going into our update, and we're going to type move input equals get input axis raw. And we want to use vertical as the axis. Now we'll go into our declarations and we'll set the move input to be a private float. And then we'll need a public variable called forward speed to multiply our input so we can control how fast the car will travel. So back in our update, we'll take our move input and say times equal forward speed. Now we'll be using this to move our sphere, and since it's a physics object, we'll need to create a fixed update function. And in here we'll say sphere RB.add force. And we'll say the force we want is transform.forward times move input. And as an extra argument, we'll use force mode.acceleration since we're dealing with vehicle type physics. We'll save and go back into Unity and test. Let's go to our forward speed variable and we'll set that to be something like 200. We'll see that it works, but we're going way too fast. So now what's the problem? So in our script, we're actually moving the sphere and having the car follow. So let's say we're moving forward. First the sphere moves forward, but now when the car follows the sphere moves even farther forward, and this puts the car in sort of a position where it's always playing catch up and hence getting faster and faster. So this is an easy fix. In the start function of our script, we'll just say sphere RB.transform.parent is equal to null. And this simply detaches the sphere from the car. So if we go back into Unity and test again, Now you'll see that we're traveling at a more reasonable speed. Now let's make our car move slower in reverse, and give the player the ability to turn the car because that's important. So let's make a doppelganger of forward speed called, you guessed it, reverse speed. And we'll jump back in our update. Now we could write out this long if statement that says something like, if move input is greater than 0, then we're going to move forward, and this would be move input times equal forward speed, else you're going backwards, so we'd do move input times equal reverse speed. But there's a cleaner way to do this. Up here we still want move input times equal, but we'll erase this and instead put move input is greater than 0, question mark, and then we'll type out forward speed, colon, reverse speed. This is known as the ternary conditional operator. So the condition is move input is greater than 0, and if it returns true, we'll use forward speed, and if it returns false, we'll use reverse speed. Now we'll go back into Unity to test, and we'll set this new variable to half the speed of forward, so that'll be 100, and we'll hit play to test. And that looks like it's working well, so let's go ahead and get our turning set up. So we'll set up a new float called turn input, and a new float called turn speed. We'll go into the update and grab our turn input the same way we grab our move input, only this time we'll be using the horizontal axis. So we move the car forwards and backwards with the sphere in the fixed update. But doing that with rotation would be a bit tricky since spheres tend to act a little crazy. The other method we have is to move the actual car. If we rotate the car, but move forward and backwards with the sphere, it should work. But what if you're thinking, well, the sphere isn't a child of the car after the game starts, so it won't rotate with the car anymore? Well, you'd be correct, but if you check out where we rotate the sphere, this transform.forward is actually the car's transform.forward. So we're still good by doing it this method. So since we're dealing with the car again, and it's not a physics object, we'll do this in the update. We'll use transform.rotate, and then we only want to affect the y coordinate of the car, so we'll use 0 for the x, we're going to use new rotation for the y, and 0 for the z. And this is going to be relative to space.world. Now directly above this we'll declare this new rotation as a float, and it's going to be turn input times turn speed. And to make it frame independent, we'll multiply it by time.delta time. So let's save and test. We'll set the turn speed to 150. Now you'll see that we got turning, and it instantly feels like a nice arcade style car. It's even got a nice little drift. There's two problems though, so let's address the one that's obvious. The car turns while we're sitting still. Now go back into the script. We could set up a boolean and check whether there's input or not, and only have the car turn while the bool is true, but there's a clever way to go about this. The vertical axis is returning either -1, 0, or 1. If we multiply our rotation by this axis, then we automatically cancel out if there's no input. And even better, when we're pressing forward, it gives the same value as it was before because it's multiplying by 1. And if we press backwards, it multiplies by -1 and it flips the rotation for us. This results in the car steering naturally in both directions. Now we have steering, so let's address the problem that's a little harder to catch. So to demonstrate, I've set up a couple of trail renderers on the car. Now when I hit play, you see something happen to these trails. You see that? That, my friend, is jitter. And it's almost inevitable because of the way we have this set up. The car is being affected during the update and the sphere during the fixed update. The problem is that the update can run many more times a second than the fixed update. In this example, we'll just assume it runs twice as often and you can still visualize the problem. So say we're already moving forward, the car is traveling forward because the sphere is traveling forward. Now we're going to turn left. Our first update is run and our car starts to turn left. The next update is run, and our car continues to turn even more. Now finally, the fixed update runs, and finally our sphere decides to move the same way as the car. It completely jumps over a big section of rotation, and we see this as jitter. Luckily, there's this thing called interpolation. If we go back to our scene and select the rigid body of our sphere, we can select interpolate, and this will help smooth this out. And with it turned on, you can see a big difference. Now if your race course is on a completely flat ground, then congratulations, you're finished. But if you're going to have hills and slopes, or you're getting a little crazier with ramps, we're going to need to do a few more things. Now let's dig into this other asset we downloaded, and we're going to pick out a ramp. Let's slap this in the scene and test. Okay, so the car doesn't follow the slope of the ramp, nor does it respect gravity. Okay, so it totally disrespects gravity for that matter. So in our script, we're going to fix rotation of car and fix gravity of car. And the way we're going to do this is with a raycast. So in our update, we're going to do a ground check using a raycast. So first we'll create a raycast hit, and we'll call it hit. Now we'll go back up to the top, and we're going to need a boolean to check if we're grounded, and we're going to call this is car grounded. Now back in the update, we can say is car grounded equals. Now we can say physics.raycast, and our origin is going to be transform.position. We're going to raycast downwards with transform.up, but we're going to use negative. And without assigning a direction, this is 1 unit by default. We're going to pass out our hit, and we need to make sure that it's only detecting our ground, so we don't get a false is grounded by colliding with our car or our sphere. We'll call the layer mask ground layer, and back up to the top, we'll make a new public layer mask called ground layer. So back in Unity, we'll select the ground plane, and we'll need to create a new layer and call this the exact same thing we did in the script. We'll select the ground plane and assign the ground layer, and then also to the ramp that we just made. So back in the script, below the raycast ground check, we'll add something to rotate our car to make it parallel to the ground surface it's on. We'll do this by saying transform.rotation equals quaternion. And we'll use from to rotation, which does exactly what it sounds like. We'll rotate our transform.up rotation to the raycast hit.normal, and the normal is just the direction the geometry is facing. We'll multiply that by our transform.rotation. Now in the fixed update, we'll say if our car is grounded, then you can move. And then we'll say else if you're not grounded, we want to add some extra gravity. And we'll do this by saying sphere RB.add force. And then the force is transform.up times negative, and we'll say 9.8 F for starters. So let's save and test. And we can't move. So let's make sure that our raycast is actually shooting down by 1 meter. So we're going to add in a distance argument into the raycast, and we're just going to say 1F. So I was just about to test again, and I noticed that on my car I didn't have my ground layer assigned in the script, so go ahead and do that. So now when we test, we can see that our rotation is fixed, but there's something going on with the gravity still. We'll go back into the script, and we're going to pump this value up to something like 30. Okay, that's better, but it's not quite perfect. So I can't remember if I said anything, but the sphere's drag was way too low to begin with, so I cranked it up to 4. But now that's way too much for the gravity to take effect. So we need to go back into our script and we need to change the drag based on whether we're in the air or not. So back up to the top, we're going to make two public floats. One's going to be called air drag and one's going to be called ground drag. So let's go down to the bottom of our update, and underneath where we rotate our car, we're going to say if its car is grounded, sphere RB.drag equals ground drag, else sphere RB.drag equals air drag. Now on our car, on the car controller, on the air drag, we're going to use a value like 0.1, and for the ground drag, we're going to keep that at 4. Now let's save and test, hopefully for the last time. And that looks pretty good to me. Now you have the basics to an arcade car controller, drifting included. You can get the exact feel you want by messing around with a combination of the sphere's rigid body settings and the other settings that we coded ourselves. And you can add tons of other things: tire marks, headlights, exhaust plumes, having the tires rotate, etc., etc. Have fun, go wild. Until next time, SpawnCamp out.